So today I'm going to talk about non-thermal dark matter and baryogenesis. And a brief outline, as you noticed probably from the title, it already has two parts. So non-thermal dark matter and also like baryogenesis. Ideally, I mean, there would be a third part which is also important and like basically connecting the scenario, I mean, to observables. I'm not sure how much of like these first two parts I can cover now. I'll stop whenever the chair session asks me to, and then I mean, if there is time, I mean, probably we can continue in the afternoon. And just to set the note, when we say non-thermal, I mean, it basically refers to a broad range of processes. Anything that happens out of equilibrium is non-thermal. But particularly for like this talk, what I really mean by non-thermal is dark matter production during a phase which is not radiation, the universe is not radiation dominated. So for example, a period of early matter domination to be specific. So this is basically what I mean by non-thermal in this talk. So I mean, so the main part, focus of the talk is on these two pieces of the cosmic pie, dark matter and also ordinary matter. So of course, I mean, the questions interesting for particle physics is like what's the identity of dark matter and how a non-zero baryon asymmetry was produced. And also relevant to the thermal history is like how, I mean, these abundances that we infer today basically were set. So the standard scenario like for production of dark matter has been this thermal freeze out, and that has been driven the field maybe for now over 3 decades. And the idea is like that dark matter particles start in thermal equilibrium at sufficiently high temperatures. For example, let's say temperatures well above their mass. And then they are subject to Hubble expansion and also interaction with light particles like standard model particles. And eventually, as time goes on, universe expands, temperature drops. So we get like to this phase, which is the thermal freeze out. And in order to get the correct abundance, this is the nominal value for the annihilation rate that is needed. And if we make a simple parameterization of the annihilation rate, then basically we get to the WIMP miracle. So these two numbers basically are the important ones, because for the typical WIMP masses, then freeze out happens like about 10 to the minus 7 seconds or earlier than that after the Big Bang. So of course, in principle, this is a very attractive scenario because first of all, it is predictive. You just start with thermal initial condition and run sets of Boltzmann equations to follow, I mean, the evolution of the system. It's also robust because as long as you start at a temperature above the freeze-out temperature, I mean, you don't care about what happened earlier on because everything is already like in thermal equilibrium. So, I mean, you don't care about the initial like reheating temperature after inflation and so on. However, related to the two numbers, the annihilation rate nominal value and also like the typical freeze-out time or temperature, there are two considerations. First of all, the annihilation rate now is being constrained like by experiments. So you get, of course, I mean, not in a completely model-independent way, but basically the annihilation rate, I mean, like we get tighter and tighter constraints. But more importantly, I mean, the having freeze out during a radiation-dominated phase is an assumption because it happens much earlier than 1 second. And currently, we don't have an observational probe of the universe before 1 second. So BBN like is a probe of like about 1 second or so. But before that, I mean, we currently have no, I mean, a probe. So once and if dark matter is discovered and properties better known, I mean, it could be like a probe at much earlier time, and hopefully like with primordial gravitational waves, we can go even like much, much earlier. So I hope, I mean, I've been able to convince you that in the light of these two considerations, alternatives to the thermal dark matter are well motivated. So just to show you these limits, these are not the most recent. These are like from Fermi 2015. But I mean, the more recent ones are more or less the same. The vertical axis is annihilation rate. The horizontal axis is the dark matter mass. And the assumption is that dark matter annihilates mainly to one of these channels. So the solid line is like a, I think, 95% confidence level. Above that, it is ruled out. And we see that, for example, this nominal value is this horizontal dashed. So there is a range of masses, above which is currently ruled out. Of course, one has to take it with some cautious, because this is like annihilation rate today, but when we talk about thermal freeze-out, this is the annihilation rate then at much earlier time. So if we have things like co-annihilation and so on, these bounds cannot be directly applied, but nevertheless, in the simplest scenario, let's say it is SF annihilation or so, then we can directly translate this into bounds on the early kind of a time annihilation rate. So basically, this is just to show that we get, better and better bounds, on the annihilation rate. So if somehow, at some point, we know definitely we are below, then it means that thermal freeze-out, at least standard thermal freeze-out in radiation domination, does not work. From a theoretical point of view also, this is the second point I mentioned. Assumption of a standard thermal history is merely an assumption. So this is like a cartoon of a standard thermal history. So inflation at some point ends. We don't know exactly the scale of that. And there is a reheating. Reheating is also model dependent, but at some point, the idea is that the radiation dominated universe is established. And in the standard thermal history, it goes all the way to about 50,000 years after the Big Bang, when the dark matter or total matter dominates. And the universe is in a radiation dominated phase. Non-standard thermal history, it's like anything that is different from this, so it's not all yellow. And a well-motivated scenario is like an early period of matter domination, which I call EMD from now on. So for example, we can have long-lived scalars like moduli, or maybe so we have long-lived heavy particles that may be produced thermally and then dominate, and then they drive a phase of early matter domination. So this end, the beginning of that, can go all the way to the end of inflation, but the lower end of that, cannot be after BBN, because we know from BBN that the universe must be in the thermal equilibrium phase at that time. So the talk today basically focuses on such a period and the implications for dark matter production, right? So the end and the beginning, are not known from any other observations, but basically we see the consequences. So now let me specifically focus on non-thermal dark matter from early matter domination. And for simplicity, let's consider a scenario that happens, for example, in some explicit string constructions. Moduli field, scalar fields phi, have a mass m phi, and they have m Planck, or in any case, very suppressed couplings to matter fields. So then we can just parameterize the decay rate like that with a constant which can be order 1, maybe order 0.1, order 10. It's difficult to get it very, very different from 1. And the dynamics of the field is like that. So the field is light in cosmological sense, much lighter than the Hubble rate during inflation. So it means that during inflation, it's displaced from its true minimum. And therefore, there is some energy stored in the field. The post-inflationary evolution basically is that the field is more or less frozen, moves slowly until the Hubble rate drops to the mass, and then it starts to oscillate about its minimum of the potential. And the simplest case is just considering m squared phi squared type of potential around the minimum, and then these oscillations, when averaged out, behave just like pressureless fluid or non-relativistic matter. And since they behave like non-relativistic matter, they can eventually dominate over the radiation which is already existing, because the decay rate is significantly small. So they have enough time to dominate before they decay, and eventually they decay. And once they decay, since they have already dominated, then they reheat the universe, and the entropy that is generated dilutes everything that was existing before. So based on this parameterization, the reheating temperature can be written something like that, and 3 MeV I have taken out because that's the minimum reheat temperature we need in order to get everything consistent with BBN and CMB. So the universe must be thermalized when the temperature was about 3 MeV. So it means that if we have, in this simplest picture, if we have something that is heavier than 50 TeV, then that can drive early matter domination period successfully. So what about the production of dark matter? So these are just the two main equations for the energy densities, matter and radiation. So here matter, I refer to the field that drives early matter domination. Radiation, everything lighter that is produced from the decay. And for simplicity, I mean, we assume that everything like which is produced instantly, I mean, thermalizes. It may not be the case, but they will still be relativistic anyways. So this is the equation for the decay of like the matter component. And this decay feeds like radiation. So this is like the equation for the radiation. And then, I mean, we can just solve. And this is what we get. So the matter component energy density decreases rather slowly. But when we get like to the point, Hubble time is on the order of like the decay rate exponentially falls. So at that time, you can say it's basically completely decayed. And it fits the temperature, so the radiation. So I mean, the radiation, basically, we see, actually, I mean, temperature decreases as the fourth root of the Hubble rate, as opposed to the second root of the Hubble rate, but that happens in a radiation-dominated phase. So here, I mean, anything that might have happened like earlier on, and so like a memory, for example, from like earlier radiation or so, I mean, I forget. So this is like the solution for the steady state phase. So temperature goes as the fourth root, so much more slowly. And now we can solve the equation for the number density of dark matter. So this is the standard like term that existed for interactions with lighter particles. But now here H now is like proportional to the fourth power of temperature, not to the second, which happens like in a radiation-dominated phase.
So when you solve these differential equations, you put as initial condition that the radiation energy density is 0 at the beginning?
For this particular graph, it is 0, so it just goes up and then drops. But of course, I mean...
but in the figure you showed before, you say I have inflation and radiation, and then there is a model.
Yeah, I'll come back to this. Yeah, so that's actually an important point. And then we also have this additional term. And this additional term is like from the direct decay of the phi field to the chi field. Because now, I mean, the decay, assuming that the phi field has a branching fraction like shown by this to the chi field, then, I mean, it's also directly produced like dark matter particle.
Arrange non-thermal conditions, you need to have a small coupling, right? You need to have a weak interaction. Which ones are actually weak?
Well, here, I mean, that's why I define non-thermal. So non-thermal, I don't necessarily need very small couplings because I don't mean they are out of equilibrium. So when I mean non-thermal in the context of this talk, it refers to like everything happening in a phase that is not radiation dominated. But I mean, the couplings could be very small, so they never reach equilibrium, or they may be large, so they reach equilibrium, but with this instantaneous thermal bath. So I think it will become clear like next couple of slides.
Produced by inflaton decay.
These are produced by the decay, and these are produced from the thermal bath from inflaton decay. So both contributions.
BR could be 0 and still.
BR could be very small, and then I mean you can still, yeah. So I mean both the terms are there, so one of them can dominate the other one.
So the lifetime of phi, so phi will decay after the thermal freeze out.
That's the whole point, because if it happens before, then I mean we are back to the standard scenario. Yeah. So that's I mean why you need like a small gamma phi, and then I mean Planck suppressed couplings help.
Okay.
So now first the production from thermal processes, and I refer like to this term. And as like Sasha pointed, I mean it depends on like how large or how small this interaction rate is. So this is the standard like freeze out, but this is a freeze out during a phase which is not radiation dominated. So most of the energy is like in some matter component. So we have like a, if you will, I mean for the same temperature, we have a larger expansion rate. So this is the thermal freeze out, and then as usual, I mean the abundance goes up with like as we decrease sigma v. And then one can get this approximate like expression. Of course, I mean, this cannot indefinitely like increase because at some point, I mean, the interaction rate is so small that, I mean, the particles, I mean, were not even in equilibrium earlier on. So then we switch to the freeze-in like scenario. And freezing, it means that they are just produced, but like they never reach thermal equilibrium. So as expected, then the abundance rises as sigma b increases. And then we have like a turnover. So that's like when we switch from freeze in to freeze out. So just a note, because I think Genevieve will also talk about the feebly like interacting dark matter or FIMS tomorrow. So it's different in the sense that here, I mean, the assumption is like that sigma b is more or less temperature independent. And then, I mean, it means that you have some like heavy particle probably integrated out, and then we have this interaction through that. So one can have like a small Yukawa coupling, which is normalizable. So that's a typical FIMP. Or one can have a UV sensitive freeze in, which means that the sigma b actually increases as the temperature goes up. So people have also like considered that scenario. The simplest case, I mean, I'm just considering is the sigma b is constant temperature independent. So at least we can plot things without going into details of the like model. So this is for the thermal processes. So maybe like, let me digress a little bit related to Francesco's question. So remember, I mean, like the whole thing, right? All these like calculations, right, and so on, are done like in this steady state phase of EMD. So when temperature goes as like the fourth root of Hubble. But of course, I mean, now the question is that, I mean, what happens like, I mean, for example, I mean, if the EMD like has some like already details in it, or even the pre-EMD, like what happened. And this has been like some work we have done recently with my student. So there are two possibilities. During the EMD, actually more than one scalar field can be present. So one can have, for example, multiple string moduli, and since they are all decaying very slowly, I mean, they can be both present, having some energy in them. Or, I mean, like we can even have an observable sector of a scalar field present, like the Affleck-Dine field. And the second possibility is like that EMD typically is preceded by some other phases, unless this is the EMD directly like after inflation. For example, if we have a perturbative inflaton decay. But if it happens that first inflaton decays and reheats, and then some other moduli come to dominate, then there is definitely pre-EMD history. So I mean, the point is that how sensitive thermal like production from thermal processes are like to the details of the EMD and pre-EMD. And actually what we found is that the allowed parameter space, I mean, can be significantly different from like the simplest scenario. So this is an example of what we call a two-field EMD. And actually, I mean, now we have two fields. One of them basically is totally subdominant. So one could say that everything is still driven by phi in terms of energy density. But the field that is subdominant, it also decays much earlier. So one naively would think, I mean, why should, I mean, they matter? So first of all, they make a very small contribution to the total energy density, and they also decay quite early. So why should they matter? But the point is like that, what is important is the TH relation. And even though these guys are subdominant, but since they decay quite faster, then they can totally dominate the temperature of this growing thermal bath at initial times. And this is what is important for dark matter production from thermal freeze out or freeze in. So this is basically what happens. Early on, the subdominant field completely dominates like the radiation. Its decay dominates the energy density of the radiation. Then there is a memory phase after its decay. So the radiation, I mean, from the subdominant field is erased, and then we are back to this standard like H like to the fourth root relation. So we see, I mean, that compared with a standard single field early matter domination, then initially we can have a much higher temperature. And not surprisingly, I mean, what would be, I mean, like this, right? The baseline curve for like freeze in switching to freeze out. Then, I mean, the allowed parameter space, right? Depending on the details of like these two parameters, F and alpha. So we see that we can now like have a completely like a different part of the parameter space that is allowed. So it means that like even the details of EMD that one could naively think were not important, I mean, would still matter.
either achieve the right density through freeze out and freeze in?
No, no. Still, I mean, it is like this whole thing is like this side is freeze out, and then when it turns over, this side is freeze in. So now the curve is like that. But now it means that, I mean, depending on the mass, the actual density may be generated either like in this phase or in this phase. So, I mean, for example, I think you probably referred to this fact that here, I mean, you have like different like values for the same sigma, but you have different values of m chi that give you the abundance. So it means that like it could actually happen here or there. If you have only a single field, I mean, there is only one possibility. But now, I mean.
So, Rouzbeh, your scalar fields are canonically normalized, they don't interact.
Yeah. So that's just like this.
That's not what you
Yeah, but just like here, I didn't want to go like into some model details because, for example, if you have like an Affleck-Tyne field plus a modulus, I mean, that is like what will happen. So you have like two completely like different fields, one observable, one like hidden sector. Yeah, but yeah, that's, I mean, the assumption. And the second possibility is like the pre-EMD. So let's say maybe earlier on inflaton decayed, right? And then, I mean, establish a radiation-dominated phase. But now, even though at this point, the total energy density is going to be dominated by the modulus over the radiation, but the amount of radiation, right, that we see for a while is still like what we started with, not from the decay of this modulus field. So now we have, I mean, a similar kind of like a memory phase, right? So this is radiation that was kind of like from inflaton decay, and it takes some time for that to just like drop. And then the radiation we get in this phase mainly from the modulus decay. So now we have an extended memory phase, and it could actually be a very extended period. And this does not affect the freeze out side much, because we know that T freeze out is roughly order of magnitude below the mass. So if even we have deviations, right, very early on, which means very high temperatures, it can only affect freeze out for very, very like large dark matter masses. But for the freezing, it is not the case, because for the freezing, then even kind of a light dark matter masses, the abundance might be like produced from like very early on, like at very early on times. So just like to show, I'm skipping the details to get like to the other parts of the talk. So now this is what happens. So this is like, again, the baseline curve. And here I have not shown all the way like going to the peak and then turn like around to go to the freeze out. But as you see, I mean, the freeze inside now is very sensitive to the pre-EMD details. And now we can have completely like different parts of the parameter space, I mean, to be allowed. In particular, I mean, this is something interesting, this almost horizontal lines. So because the temperature dependence like on H goes from 4th root to like H to the power of 2/3. Actually, I mean, even for very small annihilation or like interaction rates, dark matter particles actually could reach thermal equilibrium at very early times. And once they reach like equilibrium at very early times, then I mean, this is like this horizontal part of that. So it's going to be completely independent from the annihilation rate, because initially they reach thermal equilibrium, and when they freeze out, they already like carry the thermal equilibrium density, and then there is a later dilution by this decay. So I mean, I just want like to basically bring this to your attention that the EMD and pre-EMD like details are in general, I mean, important. Yes.
What role plays the parameter produced by the decay? Because I guess there is something that affects the final outcome.
Yeah, so that's basically this whole thing, right? So this is like a continuous process. So the entropy like is being injected continuously. So that's why temperature, I mean, changes very slowly as compared to the radiation domination. Or if you will, I mean, you can make an approximation that everything is like all of the entropy is dumped at this point. So that's the whole point. So basically, that's why, for example, in this case, the thermal like freeze out or freezing can give you the right abundance. Because now if you notice, I mean, these are the annihilation or like interaction rates much below the nominal value. In a radiation dominated phase, you get an overabundance, But now you could interpret it like that this overabundance is diluted by that entropy, which is dumped. So that was all about freeze out, freeze in production. But of course, we can also have the direct production. That's like this, remember the second term on the right-hand side of that equation. So in general, there are two scenarios from the direct production. One can directly produce this, right? And the dominant contribution comes from production at the time of actual decay. If this combination is much greater than the decay rate, or basically the Hubble time at that point, one can still have some residual annihilation. And this is the scenario considered by many people. So here is the three dots. I mean, there are people large annihilation rates like Reno, Higgs, Zeno. So this is what people studied. And in this case, after the residual annihilation, I mean, this is the actual final abundance of the dark matter, right, that we will get. And then, I mean, we need large annihilation rates to get to the observed inferred relic abundance, because TF over TR is less than 1, right? I mean, otherwise we are back in a radiation-dominated scenario. However, if this, sorry, it's very sensitive. If this combination is less than gamma phi, residual annihilation cannot happen, right? Because annihilation rate is already less than the Hubble rate. And this is called branching scenario. And I think, I mean, the first paper I could find, or written on this is the Gelmini Gondolo paper. If you know earlier papers, bring it please to my attention. In this case, whatever is produced, since I mean there is no further annihilation, whatever is produced is whatever we will get at the end. So for that reason, that may be called branching scenario.
But if sigma and V depend on temperature, how does this branching scenario?
I think then, I mean, you have to really calculate it at the temperature, which is basically the temperature TR. So this, I mean, in a sense, you can still use it, but this must be then calculated at TR.
So locally in
Yeah.
temperature.
Yeah. So then you need really to know, I mean, the temperature dependence of the sigma V. So there are these two scenarios, right, from the direct decay. So then, I mean, we can just in order to really see what is the non-thermal abundance in the EMD scenario, then we have these two large regimes, two broad regimes. So one is the large annihilation rate scenario. Large annihilation, I mean this larger than the nominal value. And in this case, depending on whether we get residual annihilation or we do not get, the minimum of these two will be the final dark matter abundance. In the case of a small annihilation rate, as basically, I mean, the annihilation scenario cannot work at all. So what we will get is whatever is produced from direct decay plus the contribution from thermal freeze-in or freeze-out. Notice that thermal freeze-in, freeze-out contribution is very small for large annihilation rates, right? Because already it is small in a radiation-dominated universe, and if it is further diluted by the entropy release, it will be even less important. So this term is only relevant for a small annihilation rate. I mean, it is already totally negligible when we have large annihilation rate.
So Rouzbeh, how much is your scenario modified if phi also coupled to the same amount of parameters? So if we have phi also becoming to this effect.
Sure. I mean, so that's, I mean, actually, I think the main assumption, because the assumption is that it decays to a standard model fermions. And then, I mean, these standard model fermions, for example, or whatever, thermalize, and then they can contribute to the thermal freeze-in, freeze-out. So the assumption here is that it basically mainly dominates not to dark matter, but to just light standard model particles. And then that's why you will get this thermal kind of a freeze-in, freeze-out contribution. Of course, as I mentioned, I mean, the standard model particles may not thermalize instantly, because I mean, you have to compare the thermalization rate with the Hubble rate, but that will make it a little bit more complicated. Of course, there are some constraints. Let me just like briefly mention a couple of important constraints. So the first one is gravitino production, because now, in particular, if you have modulus, then modulus decaying to 2 gravitinos can like produce a lot of gravitino. So that's the so-called moduli-induced gravitino problem, pointed out, I think, first by these authors. In particular, helicity have gravitinos because of their Goldstino nature. I mean, they can be produced abundantly. And the point is that once you overproduce like gravitinos, I mean, here, I mean, gravitinos are quite heavy, so they do not decay after BBN. But once they decay, I mean, if you have R parity, they produce dark matter like at the end of like the day for you. So that way, I mean, you may overproduce dark matters from the gravitino decay. So that's one thing you have to keep in mind. So if you want to have an explicit model, then I mean, you have to check that the gravitino production from phi decay is not going to be dangerous. And another thing is that this branching must be small enough, right? For example, I mean, if we consider the small annihilation scenario, if this branching is large, depending on this, we may already overproduce dark matter. So this branching in general needs to be small. And actually, as discussed by these authors and maybe like others, so the two-body decay, right? And here branching means like branching to any, for example, SUSY dark matter with R parity conservation. This is branching decay of the phi to any R parity odd particle, because at the end of the like they give you one dark matter. So as like discussed in these papers, so the two-body decays, I mean, can be suppressed, like to odd R parity odd particles of the modulus. However, the problem is that even if you suppress that, then the three-body decays inevitably show up, because moduli, I mean, typically decay to gauge fields. And if you have a two-body decay to gauge fields, like now you can attach a gaugino, like you can have a gaugino, like a vertex, right? For example, for non-abelian. And now you have a three-body decay production of gauginos which are R parity odd. And now, I mean, this ratio is simply just like a phase space, like a three-body to two-body, like phase space, like a ratio. And in that case, I mean, this is like more or less constrained to be order 10 to the minus 3. So that's also something, I mean, to keep in mind.
Okay. So if the branch duration has to be small, I mean, so phi must be decaying to something else. And what?
Yeah.
Right. So, but that changed the assumption you made from the very beginning, no? Because phi would only couple to dark matter, but the branch duration to dark matter is small.
No, I didn't say it is only coupled to dark matter. So actually, I mean, here the point is that, or maybe the hidden assumption is that it is mainly decaying to other things, not dark matter. So I mean,
and these other things are not standard model parts.
They are.
But if they are, then it would change the, for instance, the reheating process. No.
Well, you get a thermal bath, right? But this is similar to the inflaton kind of like a reheating, right? Inflationary reheating. So let's say you just like produce a...
I know, so you won't change the dark matter bonus anyway. So
right. So how much time do I have?
Well, 5 minutes.
5?
5 minutes.
Okay, so maybe let me briefly touch upon like the second part, which is like baryogenesis, but it is more like a specific baryogenesis model like post-Phaleron. So Mariano already told us about electroweak. So now I'm going like to go post-Phaleron. So notice, I mean, another challenge, right, which I did not list because it is like, yes. It's the end of the first part. No, I didn't like, I wanted like to keep only one summary. But yeah, maybe like it's good to keep in mind that, I mean, like now you have a freedom like in principle to generate that correct abundance for a broad range of annihilation rates, but there are specific constraints. So I mean, it is not all that kind of a like a rosy kind of picture. So baryon asymmetry. So back to like Pasquale's point, modulus decay, right? The entropy release dilutes everything that was produced early. So if you have baryon asymmetry, then I mean you can find the dilution kind of a factor, And for typical moduli, the dilution factor actually is coming out to be much larger than 10 to the 10. So it means that even if you initially produce order 1 baryon asymmetry, it's already diluted. So you are forced then, to like generate again or whatever for the first time baryon asymmetry during EMD or after like EMD ends. So there are 2 ways to do this. So one is like to just generate it at the end of EMD, right? So once you produce this entropy, at the same time you produce like now baryon asymmetry and then see what happens. So in principle, you can refer it like a non-thermal post-sphaleron baryogenesis. Or maybe, you rely on a mechanism that has its own associated entropy like Afflecton baryogenesis, right? Because Afflecton baryogenesis, whenever, for example, the S particles decay, they bring their own kind of this also produces entropy of its own, the process. So, sorry?
This post-sphaleron baryogenesis is what people call cold baryogenesis?
No, post-sphaleron, universe like basically is thermalized back to a temperature well below the electroweak phase transition. Not really being not having given like a thermal bath.
I miss how you do baryogenesis in this.
It's actually on the next slide.
Oh, that?
But then I think it depends on Rinaldo. How much time you?
So you have a few minutes.
So maybe let me just, I think I don't want to take time from Pasquale and also after that launch. So maybe let me just go to the next slide and introduce the model, the Lagrangian for the model. And then, if there is time in the afternoon, maybe I can go into more details.
You're 15 minutes by saying what you are going to
So he's
Yeah.
going to lead the discussion session, so we can.
So we got like 4 talks.
So this is like a model. So we have this is like the additional so we have a standard model plus additional interactions, and here basically we adopted a bottom-up approach. So we just add terms that we need for low temperature baryogenesis. So we introduce iso singlet color triplet scalars called X, and also a singlet fermion called psi. So now X, this isotriplet, because of this hypercharge, it's coupled to 2 down-type quarks, right-handed. And then we can also add this additional term, which is gauge invariant, if this is like a singlet fermion. So now X also couples to up-type right-handed quarks and a singlet fermion. And then
Last talk we have lepton number relation, now we have baryon number.
baryon number relation, yes. And then but
Before was broken spontaneously. Now it's
the baryon number, yeah.
yeah. So in this case, it's broken.
Yeah, it's broken by like this. Or if you will, it's like a Majorana term for a right-handed neutrinos. And having only one singlet, basically, we need 2 X's in order to get decay, baryon asymmetry from the X decay, right? That's well known. And maybe let me just show you this, and then I can stop and continue if possible, in the afternoon. So as usual, we get just the interference between these 2 terms. For those interactions, there is no vertex term, so we have only self-energy terms. And then, we X can decay to both 2 right-handed up-type quarks and also up-type right-handed quark and this psi. And then, this is the expression, which is a messy, but anyways, this is the asymmetry expression for the asymmetry. And we can get maybe asymmetry up to order of 0.1 if we go into the a resonant baryogenesis limit, which you actually need in this case to get the correct baryon asymmetry.
You need resonant effects?
Yeah, resonant baryogenesis. So when we get there, we can go up to maybe 0.1 or so. That's with resonant baryogenesis. So maybe So maybe let me then just show, this last.
Any further comments, questions? No? So let's thank the speaker again. Pascal, let's go.